Welcome to my video. This is number 6A in my series. It's a follow-on to one I just did on the Work-Energy Theorem. Here I'm going to derive the Work-Energy Theorem using calculus. The last video I did it using algebra, but for those of you taking calculus, I'll do this. It's kind of an elegant derivation, I think, anyway. So we know that the work is equal to the integral from the initial position to the final position of the force in the x direction. So this is just in the x direction. It's one-dimensional definition of work. So there's our force, our x-axis, and then the y-axis is the force in the x direction. And so whatever that curve might be, this is x initial to x final. So it's the area underneath that curve. Just by the definition of the integral, that's what that is. So now to derive the work-energy theorem, what we're going to use Newton's law, the second law, F is equal to ma, and that we know that the acceleration is the derivative of the velocity with respect to time, and we also know the velocity is the derivative of the position with respect to time. So we know those from just basic definitions, and we can rewrite this as dx is equal to v dt. We're going to need that in just a second, that bit. Now, if we take f is equal to m, and we'll use this as our a, so there's dv dt, just rewriting this equation, putting in that as our acceleration. Now, if we multiply both sides of the equation by dx, what we're going to get is f dx is equal to m dv dt, that's the acceleration. We've got the dx, now we're going to use this form of the dx right here, so that's v dt. Now, essentially our t's are going to cancel out, so we can rewrite this, f dx is equal to m v dv. Just getting rid of the dt's and putting the m out front since it's a constant. Now if we integrate both sides, we can integrate from x initial to x final. But over here we got velocity as our independent variable, so it's v initial to v final. So what we're going to get is the initial position going to the final position of f of x dx. We know that's just our work by our definition right here. So we're going to get m times the integral of v dt, which is going to be m times v squared over 2, evaluated at v initial, v final. So what we come up with is our work, taking this integral, the evaluation of it down to here. Work is equal to m times v squared over 2 final minus m v initial squared over 2, which is just equal to 1/2 mass times velocity squared is our definition of kinetic energy. So that's our kinetic energy final minus our kinetic energy initially. So we're going to come up with our work-energy theorem, kinetic energy final minus the kinetic energy initial. And so that's what we're hoping to get. So there's our derivation of the work-energy theorem using calculus. It's a little different approach, and hope that gives a little better clarification for you. And thank you for watching. Don't forget to leave a comment if you need to. Thank you. Bye.